Welcome back to the one slide series on control systems unlocked. So, last lecture was about the core of Lyapunov stability. Now, I would like to talk about something very useful, so-called Barbalat's lemma. So last lecture we started with this question: what happens if your energy dissipates? When I was motivating you about the concept of Lyapunov stability, meaning like you have a car that is going forward. If your velocity decreases, you will stop at the origin. If you have asymptotic or exponential stability cases. But when you have a case like this, origin is stable, meaning that maybe you start from this initial condition, you stop maybe here, depending on v dot. Not necessarily you converge to zero, you will stay there. Then we can say x1 and x2 bounded, nothing is blowing up, system is stable, that's good. But Barbalat's lemma tells you what else you can do. Well, if you have Lyapunov stability, can we do more? Meaning that, well, let's look at this example. Let's look at this example, then I will read this Barbalat, what Barbalat's lemma says. So we have this x1 that equals to minus x2 and x2 that equals to x1 minus x2 to the power of 3 system. I have this Lyapunov function candidate that satisfies all these properties. We used this in the last class. When you take v dot x1, x1 dot, x2, x2 dot, once you insert those equations, you can pause the video and do it by yourself. It can be an excellent exercise. You are going to get minus x2 to the power of 4. Well, you started your journey, your trip with two friends, but now one of your friends is missing. You don't have a nice negative term that is looking like x1 to the power of 2, power of 4, power of 6 by some positive constant. You don't have such a term. So you have one missing friend. The best you can get in this case, since x1 it doesn't play in a role on v dot. So we cannot claim asymptotic or exponential stability. Once again, if you have a term like uh, this one, at least we can claim asymptotic stability, but we don't. So we have Lyapunov stability. Lyapunov stability tells us, as I explained at the beginning of the video, x1 and x2, this Lyapunov function won't blow up. If it won't blow up, my x1 and x2 won't blow up, right? If fv is bounded, then x1 and x2 must be bounded. At least my energy derivative tells me that. But let's say we can do more. And how we can do more, like we shouldn't give up, or we shouldn't, boundedness of x1 and x2, maybe, uh, well, they are maybe bounded, but maybe x1 or x2 might go to zero. So I need to investigate this case more. So whenever you have Lyapunov stability, Barbalat's lemma is one of the two ways to investigate this, what we mean by more. So it tells you the following: if v dot dot is bounded, this is the Barbalat's lemma, a version of Barbalat's lemma at least, then v dot goes to zero as t goes to infinity. All right, so let's continue then to this example. We need to find v dot dot. Let's calculate v dot dot. V dot dot is basically this one. I'm taking its derivative, which is 4x2 to the power of 3 multiplied by x2 dot. When you insert x2 dot equation here, you have this. Now we need boundedness of v dot dot. In this case, since based on the previous step, Lyapunov stability, since x1 and x2 are bounded functions, then this quantity on the right is bounded. If the right is bounded, the left is bounded, so v dot is bounded. And now at the step, we are using Barbalat's lemma to claim, since v dot dot is bounded, v dot goes to zero as t goes to infinity. Well, our v dot is x2 to the power of 2, so x2 goes to zero as well. So, all right. So if you give up with Lyapunov stability, you could only claim boundedness of x1 and x2, but thanks to Barbalat, we do more, saying that x2 goes to zero as well. So system is not only stable in the sense of Lyapunov, but also x2 goes to zero as t goes to infinity. So thanks to Barbalat's lemma, you can do more. You can, in terms of analyzing dynamical systems. I hope this video is helpful. Let me know if you have any comment, and see you next time.